Good morning, good afternoon, and good evening. My name is Heather Rinko-Breed, and I'm a Director of Product Marketing at Epredia. Today, we here at Epredia hope to have a fruitful discussion with you on the science of tissue processing, specifically tidal versus rotational agitation. Epredia is dedicated to laboratory professionals, and the Science of Tissue Processing webinar offers an opportunity for you to discover, gain knowledge, and contribute to educational topics that matter to you. This webinar is really meant to be engaging, so throughout the event, please feel free to send any questions that you might have to my team in the chat window on the left-hand side of the console, and we will be happy to answer them at the end of the presentation. And please note, for the best quality, make sure that you are connected to a search engine with limited windows open. And if you have any technical issues or questions, please ask for help in the chat window. I'm excited to introduce you today to our featured guest speaker on this topic, Mr. Andrew Lisowski. Andrew has almost 30 years of experience in histology and histotechnology. He is a certified histotechnologist through the American Society of Clinical Pathology. Andrew attended veterinary school and holds a master's degree in molecular biology. He has worked in histology, advanced staining, cell culture laboratories, and performed both in vitro and in vivo toxicology assays. Additionally, Andrew was a proud member of a necropsy team and has laboratory experience within the pharmaceutical industry, medical schools, and previously founded his own molecular and histology firms. Andrew's role here at Epredia is that of the Senior Technical Marketing Content Manager, and we hope you come away with a further understanding of the science of tissue processing. Without further ado, let me introduce you to our guest speaker.
Thank you, Heather, for a wonderful introduction. Let's talk about tissue processing. What is tissue processing? Tissue processing is a procedure of removing all the water molecules from the cells and simply replacing it with a medium that solidifies, which we all know would be most likely paraffin. And this process takes a long time, and we can divide this into three different steps. And these would be dehydration step, or steps, should I say, as we will learn, clearing steps, and infiltration. All steps, of course, take place in an instrument called a tissue processor. Let's take a closer look at all these three steps. So step number one is where a series of alcohols, and you can see three arrows go through the piece of tissue, so it's not step. It's several steps. The function of the alcohol in this case is just simply remove water in all the cells. Next step is the clearing step. This is where solvents such as xylene, the most popular solvent in the world, is being brought in, and the function of the xylene is simply to push out now alcohol or displace alcohol from the cells. And so in the last series of events, liquidified paraffin or molten paraffin comes into play, and it now displaces xylene. So such tissue now, or specimen, is fully infiltrated, penetrated by paraffin, and ready to be embedded. Let's take a closer look at each of the steps. Step number one, dehydration. This is where, as I mentioned, alcohol comes into play and displaces all the water molecules. And alcohol is used because the paraffin is not miscible with water. So hence, we need alcohol to push out the water, and this process is carried out by immersing specimens in a series of alcohol. So when I say series of alcohol, What I mean is that not only more than one, of course, but those alcohols need to be of a progressive concentration. To avoid excessive distortion of the tissue, we need to use alcohols that would raise in a concentration. Typically, we would start with 70% alcohol and end in several changes of 100. This is done to avoid precipitation of the formalin salts that we could observe if we start dehydration with the alcohol that, let's say, starts with the 80 or 90%. So we need to do it very slowly, very gently, to avoid, again, the distortion and to make sure that we remove all of the water molecules from the tissue. Since paraffins and alcohols are not miscible, we need to use a solvent or a solution that would be miscible with both. Hence the intermediate solvent, such as xylene, that is miscible in both. Such solvent displaces or dissolves or pushes out the alcohol from the tissues in a process called clearing. The term clearing does not mean that this is a solution that we use to clear the previous solution that we used or alcohol. Clearing terms means or relates to how clearing agents such as xylene, they impart the optical clarity or transparency on all the tissues that are being processed. And this is due to the high refractive index. If you would make an experiment and stop the processing after the xylene or clearing steps, you would be surprised to see how the tissue actually look like. They do look somehow transparent or clear. Hence the name clearing step, and the agents that we use for that step would be called clearing agents. Another important function of all the clearing agents is the ability to remove adipose tissue from the specimens. Adipose tissue is a part of the biological barrier which prevents or slows down the paraffin infiltration. So by having xylene there is just additional benefit, and especially when we process fatty tissues, facilitates the processing. To make sure that all the alcohol molecules are removed, we of course need to use more than one round of clearing. Usually it is 2, ideally 3 different rounds, to make sure that there's no traces of alcohol left. And of course, goes without saying, we need to change those solvents often to make sure that the fresh, clear of any carryover last step of xylene is used. The last step is the infiltration step, and this is when this is where a specimen now is infiltrated by the liquidified or molten paraffin. The molten paraffin then solidifies, and we are ready for the next step, which will be an embedding step. We all know there are many different paraffin types on the market, and we can regulate the structural supports by choosing a right product and by learning a melting point, perhaps the amount of polymers or any additives that are in that paraffin. We can make a smart choice which paraffin use for the best results. Just like 2 previous steps, this step is no different. We need to use multiple changes of solution, so at least hopefully 2, ideally 3 changes of paraffin would be required for the optimal displacement of the xylene, and complete penetration. And also worth mentioning, if you employ vacuum, if you're using a tissue processor, the smart thing would be to add the vacuum to it, since a vacuum enhances or speeds up the paraffin infiltration. So we have spent last a few minutes talking about the process itself. What about the reagents that you need for the process? So I created a couple of the slides. Next 5 minutes, I will try to go over all the reagents needed and maybe basic differences between them. So what you're looking at is the first series, the dehydrants. You can see there are different dehydrants being used around the world. Ethyl alcohol, methyl alcohol, isopropyl alcohol. These are the most popular alcohols. I've seen butyl alcohol being used. Acetone, very harsh. It is also used as a dehydrant. Not my favorite, but I've seen people use it. Ethyl alcohol, methyl alcohol, and isopropyl alcohol, the top three. If you mix them wisely, you would create a reagent alcohol. This is something popular lately in the last 10 years. People will get away from processing only within or in ethyl alcohol. So reagent alcohols are the alcohol that would contain 90% ethyl alcohol, 5% of methanol, and 5% or isopropyl alcohol. Isopropyl alcohol also could be used as a standalone reagent. We all know this is a fantastic reagent or dehydrant to be used for small tissue biopsy. It's good for microwave processing. It's good also for xylene-free processing. So there's a lot of different changes you need to be smart about which dehydrant you use. Keep in mind that these all have different functions, characteristics, and they dehydrant also on a different rate. So make your choice, educate yourself, look up which alcohol would be best for you. Okay, let's move to solvents or clearance. As you see, there's also a variety of different compounds or chemicals. The top three, xylene, toluene, and benzene, these are called aromatic compounds. And that's not because they have a pleasant aroma, because some of them are actually odorless. Aromatic compounds are the ones that have the benzene ring in their structure. And all the chemicals, all the solutions that would have this benzene ring would be called aromatic compounds. So these compounds are very popular. Xylene, of course, the most popular, probably the most popular cleaning agents around the world. Toluene is also a very good choice. It is twice safer than xylene, actually. All those aromatic compounds, however, they display a severe toxicity. They're very toxic. They are all suspected carcinogenics. They are mutagenic, so you have to basically apply all PPE when you handle them, work under the hood, wear the gloves, of course the lab coat, so you have to be very careful around them. So these are aromatic compounds. On the other way of spectrum, if you look at all the way to the bottom, aliphatic hydrocarbons, these what we know as xylene substitutes, the safer alternatives to xylene or aromatic compounds. Aliphatic hydrocarbons are a mixture of aliphatic different hydrocarbons, and these agents, however, they have a intolerance to water. So they're not as forgiving to water or carry over water from alcohols. So they need to be changed or rotated more often. So while they are safer alternatives, they're not as robust and working as fast as the aromatic solutions. Chloroform, very high volatile compounds. I've seen it used on the tissue processors, not my favorite. Nevertheless, people do use that. It's also a solvent. limonene reagents. These compounds are cyclic terpene hydrocarbons. They are based on D-limonene, which is a naturally occurring biodegradable solvent and degreaser. This D-limonene is extracted from the peel of oranges, so it's 100% natural, environmentally friendly, and of course non-toxic. However, it comes at the price. So you might say, well, this is a wonderful solution, or solution to the toxicity of the aromatic compounds, but limonene reagents or limonene-based reagents are, some people are hypersensitive to it. So, and they display this allergic reactions as a migraine. So some people cannot be around this compound. So you have to be very careful when you're choosing this solution for the lab. One more thing about toxicity. People would ask us all the time, how do you know that aromatic compounds are more toxic than aliphatic or substitutes or xylene substitutes? How do we prove that? So there is something called LD50. LD stands for lethal dose 50, LD50. This is an acronym, and that's the number. Then you can look up actually on SDS of any of the solutions, chemicals, and the drugs that you actually buy. All those chemicals, they do have LD50s. If this is something volatile, that would be inhaling, or the LD50 for inhaling. If it's a dermal compound, that would be a dermal LD50, and so on. Anyway, you can compare LD50 or toxicity levels for any of these compounds. So if you compare LD50 for aromatic compounds to xylene substitutes or aliphatic hydrocarbons, you will learn that the substitutes are 3 times safer. It doesn't mean that they safer. And that also goes to limonene reagents, they also safer. So, yeah, so that's a variety of solvents, so be smart. Just keep in mind the aromatic compounds are really robust. They work very fast and efficient. However, they are very toxic. Last group of reagents that we would need on the tissue processor are infiltration media. And you can see here on the charts, people would use gelatin, they use a variety of resins. Although the most popular nowadays are paraffins, as we know, with high MP for melting point, or paraffin with low melting point. We also have paraffins that with several additives, such as DMSO, dimethyl sulfoxide. So the paraffins are a mixture of purified wax, and some people would call them inaccurately waxes. These are not waxes, although wax is the main ingredient. These paraffins, they do contain wax, but also other additives, such as plastic resins, or people call them polymers. Some of them contain antioxidants, some might contain dyes or other additives like DMSO. Now, by playing with the different amount of polymers and antioxidants, manufacturing can make the paraffin with a higher or lower melting point. Why is it important? People in the lab can use the paraffin with the low melting point when they are processing delicate tissues, for example, small biopsy-sized specimens. High melting point would be popular in APEC region, where transportation of the paraffin is important, and people don't like to have the pellets melted actually together. Also, high or low melting point means usually the amount of polymer that is in that product. Usually for infiltration or for the paraffin that we use on a tissue processing, we would opt for the paraffin with low melting point. We'll talk about it in details in other webinars, but this is what you would prefer actually for the tissue processing. Paraffin containing DMSO, this is a very interesting story. That about 20 years or so, someone had this brilliant idea of adding this very small tiny molecule, dimethyl sulfoxide, to a long chain of paraffin of wax. And what the DMSO does, it crosses the cell wall very efficiently. Scientists still don't know how is it possible to happen, because it basically crosses it very, very efficiently in no time. So the idea behind the DMSO and paraffin is you attach DMSO to long a chain of wax to help penetrate tough tissue. So if you are processing fibrous tissue, tough tissue, dense tissue, maybe this is a good option for you to use a paraffin with DMSO to help penetrate and infiltrate such tissue a little better. So these are a lot of choices within the paraffins, and actually a big topic for yet another webinar. So we've talked about processes, we've talked about reagents. Let's talk about the processing methods. So we all know there are basically two methods, manual and automated methods. So manual processing method is very slow, labor intensive, since transferring or changing reason takes time, and it's all done by hand. With the advancement of instrumentation, automated instruments, this method is almost now obsolete. Let's spend just a few seconds on automated processing. So we have fluid transfer, specimen transfer, and microwave processing. The most popular method is the fluid transfer. So fluid transfer is the way of the instrument and closed instrument moving the fluids from the reagent bottles into the processor process chamber or a retort. So the reagents are being pumped in and out during the processing. Specimen transfer, on the other hand, they do not transfer reagents, they do transfer cassettes. Hence the name, you transfer the specimen. Such processors, we call them dip and dunk. So again, this is where the processor transfer cassettes from station to station in a rotary or a linear configuration. Lastly, we have microwave processing or microwave-assisted processing, which uses, which accelerates processing by simply heating reagents. I just mentioned that fluid transfer processing method is the most popular, and there are actually three different ways of doing it. These are the three different methods of processing. So these are tidal processing, contrast still processing, and rotational processing. Let's take a closer look on those three processes. So tidal processing is where the tidal processor utilizes the simple immersion and agitation techniques. This is where the tissue locked into tissue cassettes is stationary, and the reagents are being moved by the means of the impaler or the spinner and bottom of the retort. Contrast still processing uses the baskets that are gently rotated inside the chamber, and that provides way more effective agitation than just by impeller. Lastly, rotational processing utilizes a rotating rack to induce the interaction between fixative fluids and the tissue samples. This is where the rack rotates and moves the cassettes inside the baskets in and out the solution. If you are still unclear what is the difference between contrast stir and the rotational processing, just please look at this slide. Contrast stir processor moves the basket through the fluid on a central pivot rather than using the impeller to circulate the fluid. So the chamber is in the vertical position, and the baskets are moving 1 1/4 turns one way, and then it alternates and it moves the baskets the other way. but the chamber is still in a horizontal position, and there's no more impeller, no more stiller. The baskets are being rotated left and right. Same idea of moving the baskets rather than moving the reagents with the aid of the stirrer or impeller is used in rotational agitation. So the difference is that in this method, the chamber is tilted. It's at the 45 or so degrees angle. So the baskets are moving in and out of the solution. To better understand the rotational action, I've created this simple semi-animation. So you can see chamber is tilted to some degree, and the instrument revolves the chamber in one direction. After several turns, the processor changes the revolutions into the opposite direction. Since we now know the different processing methods, let's look at the tissue processors and methods they use. So what you're looking at are the examples of the tissue processors that utilize Tidal processing. So you can see on the left two processors from Leica. These are Peloris 3 and Pegasus. Then you have the Sakura VIP6 and the Magnus from Milestone. These processors are typical Tidal processing processors. Let's look at the Epredia tissue processors. On the left, you have the Epredia Excelsior. This is the processor that uses contra stir method. In the middle is the Epredia Rebus. This is the processor that utilizes rotational processing. And the picture would not be complete without the Epredia STP-120. This is the processor that uses the specimen transfer. Okay, so let's take a closer look at the baskets. How do they look really? So we agreed that the baskets with the spaces in between the cassettes would provide the better fluid access or tissue accessibility to all the processing reagents. The basket on the left, this is just regular baskets we all know. We all seen it, rectangular. You can see how many cassettes are tightly packed in it. And you can imagine that it will take time for the liquid or processing reagents to access the tissue. This particular basket, you can see there is no insert. So probably the insert was just forgotten, or maybe someone packed the cassettes so tightly to process more cassettes in one run. The basket in the middle, this is the basket that is being used by our Excelsior. You can see a round shape, and you can see clearly spaces in between the plastic part that creates this additional barrier between the cassettes. And the baskets on the right, these are the baskets for rotational processing or Rebus rotational processing. You can see the same idea. They are all already built-in spaces which provides this better or increased flow and speed, right? Better drainage rates. We haven't talked about that yet, which also, of course, translates into a better carryover or lack of carryover, right? And overall, better improved fluid exchange. And you can see here the yellow arrow points to the spaces in between cassettes, the spaces that you don't see on the cassette or the basket on the right. Here is another look at that basket that we used at the Rebus tissue processor, and thanks to the unique design or spaces between cassettes, we see the increased reagent movement, and tissues are processed in less time because it happens just so much faster. And of course, and I mentioned it just seconds ago, the faster drainage, right? So the carryover is reduced, which is very important. We can maybe rotate or change the reagents less frequently. Just to emphasize, you can see how the reagents, blue arrows, go through the tissue. Not only reagents have a better access to the tissues thanks to the spaces, but also, again, you can imagine better drainage. Before we talk about rotational processing, let's spend just a minute or so on how tidal agitation works. So tidal processing uses a simple tissue immersion combined with the gentle agitation. And you can see here on the right, the cassettes are stationary, and there's a simple impaler or stir that moves the reagents around. This could be enhanced by adding vacuum and pressure, as well as temperature. So higher temperature would be added, or use even of the microwave. This is another type of simple impeller that moves the reagents inside the chamber. Vacuum and pressure cycles coupled with heated reagents might reduce processing protocols, processing times, and also improve infiltrations on those hard to process and penetrate tissues. This, however, might come with the price. As we know, specifically smaller tissues, delicate tissues, can be negatively affected by the heat. And this can lead to different artifacts and eventually to also poor quality of the staining. Unlike other processing methods, rotational processing is performed at room temperature and without the heat. It also offers the advantages of the traditional processing by providing the exceptional improvement in the fluid exchange efficiency. And this is because of the fact that instead of the impeller that moves the reagents inside the processor, rotational tissue processor uses this tilted or canted chamber that moves left and right, moving the tissues locked in the tissue cassettes in and out of the solutions to induce even better interactions between the reagents and the specimens themselves. What are the most important features of the rotational tissue processor? So first, I would say this is the smart basket design that allows easy fluid movement in and out of the cassettes. Next is the idea of having a tilted or canted processing chamber instead of traditional vertical one. Lastly, the tilted chamber is only partially filled with the reagents, which allows the tissue to leave the reagents, being suspended out of the reagents, and then again, as the chamber turns, be submerged again into the reagent. How do we know that rotational processing is more effective or efficacious? Physics scientists, as well as engineers from the Western Michigan University, did the experiment or designed the experiment to compare tidal and rotational agitation methods using both types of the processors. And they look at or measure the particle image velocimetry, which translates into flow speed. And also they look at the planar laser-induced fluorescence, which translates into flow motion. So again, they look at the flow speed, flow motion, and you can see on the pictures below, they build the mock-up of both tissue processors. What those flow studies shown is that, and this is a quote from the paper, thanks to the rotation of the chamber, higher magnitude of the mixing of the reagent occurs due to the presence of large turbulence generating vortices as the cassettes are filling up with the liquid. How was the efficacy or effectiveness measured? Measurements of reagent flow speed and reagent flow motion were combined into flow fields, and these were compared and analyzed. And results showed the following. First, flow rates through the cassettes and specimens were higher, which means that more fluid is passing during the same time interval, which of course correlates with faster tissue processing. Actually, measurements of the flow fields indicate that rotational processing provides an overall 7-fold improvement in fluid exchange efficiency when compared to traditional tidal agitation processing. Secondly, turbulence and vorticity in rotational processor are 5 times larger than in the tidal agitation processor. If you wonder what those terms mean, look at the picture that came from this report. From the study of fluid dynamics, we know that turbulence is the fluid motion driven by rapid changes in pressure and speed. Vorticity is how the fluid circulates in a given area. Consequently, turbulence and vorticity indicate that a great deal of rapid, almost violent mixing is occurring between the racks and, of course, specimen in those racks. Lastly, thanks to the flow motion experiment that also included the usage of fluorescent dye, it was shown that the fluid flow direction is perpendicular to the tissues inside the cassettes rather than the fluid flow direction alongside the cassette length, which is in the case of the tidal processor. This, of course, means that tissues in rotational processor can be processed in less time, which is yet another great benefit. You are looking now at the actual results from the study. So let's go ahead and compare a few numbers. On the left column shows the calculations for the rotational processor, and on the right, you have the calculations for the tidal instrument. I added yellow stars to highlight results that stand out or can be seen as true differentiators for both processors. Please note that cassettes used in this study were identical for both processors. So first, drainage flow cycles and flow rates were approximately 160 times higher. This is an incredible difference. We know that this is at least partially due to the unique basket design. Second yellow star on the left shows flow velocity or speed at 65 millimeter per second, which in comparison to 4 millimeters per second, you see the number on the right, is about 16 times faster. And all the way on the bottom, total flow rate or combined velocity flow rate and drainage flow rate is approximately 19,000 cubic millimeters per second, as compared to around 3,000 cubic millimeters per second. When calculating the flow rate ratio of RTP and tidal instrument, it is exactly 6.7 to 1. And this is the overall 7-fold improvement in fluid exchange efficiency I have mentioned a few minutes ago. I have used one of the tables from the reports from the study that the University of Michigan did, and I converted into a chart. This, in my mind, shows a little better. We can understand a little better the timing differences between two different methods of processing. On the left, you see the times for the processing of a very small tissue, biopsy-sized tissue. On the right, we see the times for the processing more standard size tissue, around 5 millimeter. And you can see on those bars, they represent 4 different processor types. On the left, you have the rotational processor. Second to the left, you have the contrast stir processor, which is Epredia Excelsior, and 2 unnamed Tidal processor. They just call it A and B. And if you look at the chart on the left, you can see clearly the difference in time that could be saved due to the method. So 109 minutes on average to process a tiny piece of tissue versus, let's say, 134 or 225 minutes. So it's a remarkable difference. Also, if you look at the chart on the right, you can see the difference is even more pronounced, 400 minutes or so for the rotational processor versus 750 and 722 for a tissue processor. So clearly the times are much better. The protocol could be shortened, and so we can maybe process more or save time in the lab. What makes an effective tissue processor? So number one, the ability to effectively move the reagents in between cassettes and the baskets. Number two would be the same ability to move the reagents now within the retort. And number three basically takes those 2 above and tells us if we can do that, we can maximize lab productivity by rapid or faster processing. So let's summarize the last 45 minutes. The Epredia Rebels tissue processor has this unique canted chamber design. It is the only premium tissue processor on the market of this kind that allows for the rotational agitation within its chamber. And as I mentioned already, this design, this unique design, enables us to process approximately 7 times faster than the traditional processor without the need for added heat.
Hello, everyone. Thanks for attending. This is Lindsay Imgrand, and I am the Regional Tissue Processing Manager for the Americas. I have joined this webinar to help answer questions that you have put in the chat and send them off to Andrew so he can answer any questions you may have in regards to this presentation or tissue processing. The first question we have is, how is the rate of reagent flow through a cassette determined or measured?
Thank you, Nancy. So I guess my turn to talk. So thank you. I see the questions were posed by Richard. It's a very good question. So how is the rate of reagent measured? So simple. That was the ingenious way of thinking by the scientists and physicists actually at the University of Michigan. What they did, they added fluorescence dye to the solutions in their mock-up instruments. And they were able to measure the fluorescent particles with the timestamp. So they would look at the tissues. The tissues would be removed from the cassettes at, let's say, 15 minutes, 30 minutes, 40 minutes, etc. And they would measure the amount of fluorescence that was originally in the liquid to see how much of it is already in the tissue. And this way they were able to measure the speed on the rate with which any reagents would go through the tissue inside the cassette. So that's how they did it.
Thanks, Andrew. The next question is there a link available for LD50 information?
So there's no link. LD50 for lethal dose 50. So those numbers are posted but any government site. So I believe NIH, National Institute of Health, FDA, any chemical government site would post it. If you really want to quickly access of LD50, for example, of xylene or anything like that, any SDS or SDS should include that information. LD50 is the simplest toxicological screen, and those numbers, whether this is inhalation LD50 or oral 50 or dermal LD50, those numbers should be included in, I believe it's section 17 of SDS, toxicological data. So there's no a link per se. You would have to type maybe into an internet site or actually the net, let's say LD50 off toluene or whatever you want, and that number would be given to you. Or, as I said, look up SDS documents that are posted on the website.
Thanks, Andrew. The next question is, how does the basket design aid in tissue processing?
This is a simple one. So the basket design, we all know the baskets, they are steel baskets, plastic baskets. They might have different shapes, different height. The baskets come with inserts that was originally designed maybe 10 years ago. So the bigger spaces or well, I guess this is the good word, the bigger places between cassettes that would warranty the better exchange, the flow rate and exchange between tissue and a liquid. So Revos baskets are, for the first time, designed the way that they have built-in spaces in between cassettes. So you can't really cram the cassettes next to each other. As we know, this will impact the flow or exchange rate. Now you have those spaces where the liquid, whatever it is, alcohol, solvents, or paraffins, will have a better or easier access through the holes of the cassette to the tissue. So in my mind, this is crucial. And also think about it, the spaces that are created thanks to this design also aid in a drainage rate. Drainage rate translates into the carryover. So the better drainage rates, the drainage rates on Revos basket are just phenomenal. They are just so much better than anything out there. So that means less carryover, less changes of reagents, and better processing.
Thanks, Andrew. The next question is adding heat necessary in tissue processing?
Question worth $1 million, right? So yes and no. So everybody pretty much out there use a little bit of heat, right? Very few people use ambient temperature. People, especially these institutions, hospitals, big reference labs, every minute counts. So what people would usually do, they would add heat to the processing protocol, a gentle heat, 37 degrees Celsius, sometimes 45. Some people go as high as 55. Now, does that increase the rate of processing? Absolutely. It's simple physics, right? The elevated temperature means less viscous liquid. They would go through the pores of the cassettes, through the samples locked in the cassettes a little easier. However, if any of those tissues are biopsy size, small pieces of tissue, the added heat might and probably will impact the morphology. In extreme cases, thermal damage, spacing in between tissue cells would be created. So is heat good? It's not really good. It only aids in speed. So if you have a luxury of going a little slower, I would recommend removing heat altogether and process on a ambient temperature. Now, with this revolutionary processing, rotational processing, when we see the rates of the exchange or rates with which the reagent goes through the tissue, now it's so good. You don't really actually need heat to speed anything up. You can make up with this process or with this new idea and just completely remove temperature out of the equation and do not risk creating a thermal effect. So while heat, yes, it can speed up the process. Now with Revos, you can do the same thing without adding heat.
Thanks, Andrew. That's helpful to know. The next question is, how does volume flow rates affect processed samples?
Well, so flow rates, right? So the faster that flow rates means how the liquids, the reagents, the alcohols, the organic solvents, and paraffins go through the tissue. And it's a complex question because you might aid in a reagent exchange by using a better, let's say, basket, right, with those extra spaces. So you aid in a flow rate. Also, and this is where we want to talk about today to you, is the rotational processing, which is just a completely different thing in terms of fluid dynamics by creating this extra speed and vorticity, which is really means curl of the reagents that access the tissue a little better. So the better the flow rate, the more effective is the processing. So imagine now a fibrous tissue or a dense tissue um, that is otherwise not easy to process. Now, with the increased flow rates, you are processing the tissue more complete. And so the times could be shortened. So that's the flow rate. So a better flow rate, and the flow rate, I'm going to get into the numbers and give you an example, not to be just to be precise. Flow rates, which is really the speed of the liquid that go through the tissue, that was measured by those physicists at the University of Michigan. Flow rates at the rotational tissue processing are about 65 millimeters per second. Now, anything tidal processing, which means all the other processes that we know today, they about 4 millimeters per second. So think about it, it's multiple times more over faster. And so flow rates are just crucial in terms of accuracy of the processing, penetration, infiltration of the tissue, especially those hard to penetrate tissues. So in my mind, flow rates, the higher they are, the better processing you have.
Thanks, Andrew. Here's another question that has to go with flow rate. Is there a requirement to place cassettes in a certain order so the flow rate is not impeded by different sizes of tissue?
We'll have to think about this one. Is the requirement for place? So I would say no, because all those baskets, I'm thinking now the Revos baskets, those triangular baskets with the spaces. So while that would be important in a standard size basket that, let's say, other companies are using, the square steel baskets, and you have, 3 of them on top of each other, you would think, or you would expect the tissue locked into, let's say, the top basket right in the middle will not get the same amount of attention, if you will, than the cassettes that are positioned outside. And you compensate with time. So instead of maybe going 6 hours, you'll go 9, just to make sure that every tissue will enjoy the same rate of attention or processing. With Revos, with those spaces added, every cassette has the same amount of access to the fluid exchange. So in my mind, there's no requirement. You can place them whatever you like, in any order you like, and they should receive the same amount of processing or attention from all the reagents.
Thanks, Andrew. The next question is, in case of an adverse event like a power run, will tissue suspend in the air dry out?
So two things, right? So this is the tissue processor that for the first time allows the tissue leave the a solution. So as the chamber rotates, the tissue, the cassettes with the tissue in them go in and out of the solution, which creates a question. What happened? What happens if there's a power supply, a mechanical failure of the tissue processor itself, and the cassettes that are outside of the liquid are now suspended in the air? Will they dry out? So first, two answers that I would get for you. So for the first thing is that in a case of power failure, this tissue, the specific tissue processor, unlike many others, it has a built-in battery, and this is not something that a customer needs to purchase separately, because people do it all the time. They spend a lot of money, so that would be called UPS, uninterrupted power supply. Now Rebos has this built-in. It's a 3-hour backup. So in case something like that happened for 3 hours, the tissue will continue to be processed. If this is still not enough, or the failure was caused by something else, and the tissue is actually locked, in the air, think about it. This is all happening under vacuum and pressure. And there's so much humidity inside the chamber. It's basically 90% humid inside. So there's no way, even for several hours, the tissue will never dry out. The climate, the environment inside the chamber is so wet, it's so humid. And so, and the reason behind this air movement, air to liquid, is to create this vorticity, this curl, to increase the speed, because of the action, you increase the speeds of the reagent, the flow rate. So going back to the original question, so tissue will not dry out. There's no way that would happen in the current environment.
Thanks, Andrew. One last question, and then we'll wrap up our webinar. How alcohol replaces water in the tissue? Because both water and alcohol are polar solvents, so they will mix. The question.
All right.
So I think they're wanting to know how alcohol replaces water in the tissue.
So I think the answer is very simple, actually. Water is a dehydrant. Water pulls, alcohol pulls water out. So by exposing tissue to the alcohol, and all the tissues are full of alcohols. We are alcohols, water, I'm sorry. We are made of water, basically, right? Some organs are 90%, blood, it's considered an organ, 98% water. Bones, 40% of water. So we are full of water. Now, you take any of those organs and put in alcohol will pull, no matter if this is a polar solvent or not, it pulls water out of that tissue. It's a simple, physics. The water will go from the lower concentration to join to higher concentration. So you're pulling water out of the tissue, the alcohol goes in and ready for the next step, which is solvent. So I think that's the answer.
Okay, sounds good. Well, everyone, thanks for joining our webinar on the science of tissue processing, tidal versus rotational, and look forward to many more webinars to be hosted by Andrew Lisowski. We appreciate your attendance today. If you have any questions, please send them to Andrew at andrew.lisowski@epredia.com. Thank you.
Thank you.